Hello again. We continue from the point where we ended in lecture number 1. So this is lecture number 2 for Math 609. We were discussing last time Gauss elimination, and we were discussing the case when we start with a matrix A, and let's say we will consider the two cases if we have the system AX is equal to B, and if we start with the matrix A and let us write A is equal to A. And we consider the case that every time we perform Gauss elimination, the entry of the resulting matrix that sits right here, the entry AKK, which we call a pivot element, is different from 0. If every time after we perform a step, the pivot element is different from 0, we can compute the numbers LKJ through this formula. LKJ is equal to AJKK divided by the corresponding pivot element, which, if you would like to visualize, it is the element that sits on this position, the element L that sits on this position is just the ratio of the corresponding blue element and the corresponding red element. So everything that sits on position K plus 1K is the ratio of the current element that sits there divided by the pivot. The element L with index MK is the ratio of the current element that sits on position MK divided by the corresponding pivot element. This is how we create the numbers L, K, LJK. And then using these elements, we create the corresponding lower tridiagonal matrix LK that has ones on the main diagonal and has the corresponding L's on column K below the main diagonal with negative signs. Now, we also discussed that if we start with the equation A is equal to A, then we perform one step of Gauss elimination. The performance of one step of Gauss elimination means that we multiply on the left the matrix A by the corresponding matrix L1. So we have L1A is equal to L1A. Then we perform a second step of the Gauss elimination. We can do that by multiplying on the left the resulting matrix by the matrix L2, where the structure of all the matrices LK is the following. You have 1 on the main diagonal, and below the main diagonal on column K, we have these L's with a negative sign. Then this is equal here to L2, and so on. At the very end, we have a multiplication with the matrix Lm minus 1. And here at the very end, we have the multiplication with the matrix Lm minus 1. So once we have that, as a result, the matrix that we end up with is the upper triangular matrix U, and so we have that Lm minus 1 and so on, L2, L1A is equal to this upper triangular matrix U. And in the previous lecture, we had exactly this equation, and from this equation, we discussed that this equation can be translated in the form A is equal to L times U, where the matrix L is equal to the product of the inverses of these matrices LK. We know that the matrix U is an upper triangular matrix. What we need to show is that the matrix L is a lower triangular matrix, and this is what we are going to do next. Before doing that, let's see how this works if we have to solve a system using Gauss elimination. If we multiply, so we continuously here multiply by L1, both sides of the system, then we multiply the same as we did here, then we multiply by L2 and so on, and at the end we will have Lm minus 1 and so on up to L1 multiplied by Ax will be equal to Lm minus 1 and so on multiplied by L1 times B. So this will be some new vector, which will be C, and this here will be exactly the upper triangular matrix U. So using Gauss elimination, every system Ax is equal to B can be rewritten in the form Ux is equal to C, where U is an upper triangular matrix. So it has this structure. Here is something, and on the main diagonal there is something, and everything below the main diagonal is equal to 0. And then to solve this system, we simply use the backward substitution, because the backward substitution is giving us the solution. And we know that the cost, the operational cost to solve the system using a backward substitution is m squared, where m is the dimension of the problem. Therefore, the cost to solve the whole system, Ax is equal to B using Gauss elimination, is the cost of finding the matrix U plus the cost of the matrix, the cost of solving this linear system. Now, after we discuss the form of the matrix L, we will discuss the cost of finding the matrix U, which is the cost of the Gauss elimination. So let's go further. We said that in our equations from before, we had the form for L. This is the product of the inverses of the matrices Lk. So what we have that the matrix A is the product of the matrix L and the matrix U, provided that all the pivot elements A, K, K, K that arrive during Gauss elimination are different from 0. And we show that the matrix L is actually the product of the inverses of all these matrices Lk. And we know what the form of a matrix Lk is. What our goal now is to find what is the matrix L. In order to do that, we are going to rewrite the matrix Lk in a more friendly form. And in order to do that, we will use the vectors little lk and the column vector ek, which basically is the standard basis vector that contains all zeros, except that on position k, it has a value 1. If we look at the matrix Lk here, we see that it consists of the identity matrix, and it has this part here below the main diagonal on the kth column. So I can rewrite this matrix Lk as the sum of two matrices, actually as a difference of two matrices. So the first matrix will be the identity matrix, which will take care of all the diagonal elements, and then minus because of these minuses right here. And then I will write the matrix that has zeros everywhere, except that here, if this is column K, and if here this is row K, this will be on the main diagonal, it will have 0 on this main diagonal, and below it will have the L's, Lk plus 1k, and so on. It will have Lmk. K. So this is this piece here of the original matrix. I can just decompose the matrix LK as a difference of the identity matrix and of this matrix, where everywhere else I have zeros, but on the kth column below the main diagonal, I have all the LKs. Now, if I do that, what is happening is that this is the identity I here, minus, here is this minus here, and then I would like to represent this matrix in some way. And a convenient way to represent this matrix is to write it as a product of the vector LK and the vector LK. You can think, since we're talking about real entries of the matrix, you can think of this EK transpose. So I is a matrix that is of dimensions m times m. LK is a vector column, which is of dimension m times 1. EK transpose is a vector row, which is of dimension 1 times m. And when I multiply those two vectors, I will end up with a matrix of dimension m times m. So once I multiply LK by EK transpose, I will end up with a matrix that is of dimension m times m. And what will be, so here is 0, 0, and so on, 1, and 0. This is the vector AK transpose. So if you do this multiplication with LK and EK transpose, using the rules of matrix multiplication, you will end up with exactly this matrix here that has zeros everywhere, except that on the kth column, all the elements below the main diagonal are the corresponding L's. And therefore, we have another representation of the matrix LK. Now, the first claim that we are going to prove is that LK is in fact an invertible matrix, which is not so difficult to see because this is a lower triangular matrix with ones on the main diagonal. Therefore, the determinant of this matrix is 1 as product of all the elements on the main diagonal, and therefore it will be invertible. The more interesting part is how to compute the inverse of this matrix, and the lemma tells us that the inverse of this matrix is in fact also a very simple matrix. This is the same basically as the matrix LK. The only difference is that here, instead of these minuses, we have pluses. So just we drop the minuses. This is how we can write the formula for the inverse of this matrix. So this is the lemma. And the proof of the lemma is not so difficult. So to show that LK inverse is this matrix, we have to show that the matrix LK multiplied by this matrix gives us the identity. And the same way as we will show here, we'll come back in a minute to prove that, to show that this matrix here that we claim is the inverse of LK multiplied by LK is the identity. And therefore, the inverse of the matrix LK is I plus the product of LK and EK star, where and therefore the formula for LK inverse is this. We have ones on the main, or the form of LK inverse is this. We have 1 on the main diagonal, and here we have column K, and in this column K, everything below the main diagonal are actually those L's, where again, what is LJK? LJK is AJK K divided by AK K. And again, what were those? Those were all the elements below the pivot element in the kth step. So this divided by this, and so on, this divided by that. To continue our proof, let's look at this product here. And let's write down the formula for our matrix LK, which we saw here that there is another a convenient way to represent the matrix LK. And now do the matrix multiplication. I times I will give us I. Then we have I times LK EK star is this term. Then we have minus LK EK star times I, which will give us this term. And then we have the multiplication of this term with this term. And we have to be careful that matrix multiplication is not commutative. So we have to write exactly the order in which these factors appear. So first LK, then EK star, then LK, and then again EK star. Clearly, those are two matrices with opposite entries, so we cancel them out. And we use the fact that the product of matrices is multiplication of matrices is associative. That means if I have A times B, and then I multiply the result as with the matrix C, that this is the same as multiplying A by the product of B and C. And therefore, in this product here of four vectors, which I view as matrices, I can put the parentheses everywhere I want. And so I decide to put the parentheses right here. And I want to see what this is. EK transpose is vector, which I can view as a matrix of dimension 1 times m. And then LK is a vector of dimension m times 1, right? Remember that LK here was this vector, which is the vector column of dimension m times 1. And therefore, EK times EK transpose times LK, when I do the multiplication, this is a matrix of dimension 1 times 1, or in fact, this is a number. And the question is, what will be this number? So if I have the vector EK transpose, this is 0, 0, and so on, 1, 0, and so on, 0. So here is the K. And I multiply this vector by the vector LK, which is 0, 0, and so on. On position K, I have 0 here. And then after that, I have LK plus 1K. And so on, I have LMK, right? Remember, this was the vector LK. On position K here, it is 0. So this position K here is 0. And after that, from position K plus 1 to M, it fills in with the M's. Well, if I do this multiplication, then the only place where I can have a hope of non-zero term is when the 1 will hit some entry of that vector LK, but the 1 sits on K position. So if I do the multiplication, the 1 will hit exactly this term here, which stays on Kth position, which is 0. So this number is nothing but the number 0. And this number, as a number, I can pull out. And therefore, I will have the number 0 multiplied by some matrix, which will give me the 0th matrix. And therefore, the result is the identity, which gives me that indeed the matrix LK multiplied by this matrix is the identity. In similar way, one can show that this matrix times the LK is equal to the identity, and therefore a simple formula for finding the inverse of the matrix LK is this formula. Now, what do we have? We have that the matrix L, as discussed before, is a product of these inverses. And therefore, the matrix L will be, since we found the inverses of each of the matrices LK, this will be this matrix, which is inverse of L1. Then the inverse of L2 will be this matrix, and so on, that the inverse of Lm minus 1 will be this matrix. And what we need to show what is the structure of the resulting matrix. And the next lemma tells us that the structure of the resulting matrix is this. We have the matrix L is equal to, it is a lower triangular matrix. Everywhere on the main diagonal we have ones. Everywhere above the main diagonal, we have zeros, and below the main diagonal are those exactly numbers that we have. And what are those numbers, LJK? Those numbers are the AJKK divided by a KKK. So after performing the first step of the Gauss elimination, we can fill in the first column of the matrix L below the main diagonal, because after the first step of the Gauss elimination, we will know these ratios, which is at the first step, this is my pivot element, and therefore I will have the ratio of the second element divided by the first element, and so on, the mth element divided by the first element. This is how I will get my L's, and these L's will be put under will fill in the first column of L. Then I do the second step of my Gauss elimination. In the second step of my Gauss elimination, this is the pivot element, and the pivot element occupies the second column. Then I look at the corresponding ratio of this element divided by the pivot element. This is the corresponding L with the same index with the same indices as the indices of the numerator of that ratio. And so on, I will compute all the L's that occupy the second column of my matrix L. So I will compute all these L's, and this is how I'm going to fill in the all the elements below the main diagonal on column 2, and so on. So the lemma, to go back to the lemma says that the formula for L is this, and in fact, this tells us that using Gauss elimination, we for free get the matrix L for free, get the elements of this lower triangular matrix that participates in the LU factorization of the matrix A. So to do the proof, we will first prove this product here. And then we will see, we're not going to go into details further what will happen, but we will just examine the product of the first two matrices. Again, this is the identity, because identity times identity is the identity. Then this, after that, it is L1 E1 star, then it is L2 E2 star, and then this is this matrix L1 E1 star times L2 E2 star. And as we did here, we know that we can put parentheses everywhere in this product, and we decide to put the parentheses right here. If we put the parenthesis here, what is the vector E1? The vector E1 transpose is 1, 0, 0, and so on. And what is the vector L2? The vector L2 is 0 on the first position. And if you look carefully, what was the vector LK? We have at K position 0, so it will be 0 also at position 2. And then after that, we will have the terms L3, 2, and so on, LM2. So if we do this multiplication, we'll see that the only place that one will have a hope to end up with a non-zero term, because these zeros will make everything else 0, will be the multiplication between the 1 and the first term here, which will be 0, and therefore this product here will be 0. The fact that this product is the number 0, that number can go out and will make the whole matrix 0. Therefore, the product of the first two matrices right here is the matrix I plus L1 E1 star plus L2 E2 star. Let me remind you that this means that if we look at the first product, I will have the identity matrix and so on. Then after that, L1 E1 star will populate this first column of the matrix, of the resulting matrix. So I will have here L21 and so on, LM1. Then L2 E2 star will populate the second column. So here I will have L32, and so on will have LM2, and everywhere else will be 0. So this matrix here will be exactly this matrix here. So it will have, once on the main diagonal, will populate the first column and below the main diagonal, and will populate the second column below the main diagonal, and everywhere else will be 0. And then if we continue the same way, doing the product of this matrix and the next matrix I plus L3E3 star, having similar considerations as before, we will end up that the result is the identity plus L1E1 star and so on, plus LM-1EM-1 star, which will give us that after every product, we will be continuously filling in the first column, then the second column, and so on. At the very end, we will fill the M minus first column below the main diagonal, and we will end up exactly with this form of the matrix L. Now, what is going to be the actual algorithm if we decide to program Gauss elimination? We go back to what we ended up in the previous lecture, namely those rows here that tell you how to compute the numbers LJK, by which you will multiply the kth row and add it to the k plus first and so on up to the mth row. And this is the actually multiply this number with a negative sign and then add it to the k plus first and so on to the mth row. And these two rows are programmed in here in some sort of a semi as an algorithm without any use of any particular language. So what we start with, we set that the matrix that we would like to end up with U, we set it first to be equal to the matrix A, and the matrix L to be equal to the identity, and then we gradually will populate the matrix L. And so we start for k from 1 to m minus 1, and then the index j is from k plus 1 to m. We find the elements L. These elements will be the elements that will populate the lower unit triangular matrix. And then, as we discussed, that the new elements of the matrix U, the new entries of the matrix U from position k plus 1 to m will be equal to the entries that from to the jth. It is right here. It is the same equation. The new element on position ji will be equal to the old element of position ji. The old means with index k minus this index ljk minus the times the corresponding element on the that sits on the kth row and the ith column. And here it is written in a syntaxis in which instead of having the second index running from k plus 1 to m, this tells you that the second index basically changes from k plus 1 to m. So this is the algorithm. In practice, as I discussed before, the matrices LK are never formed and never multiplied explicitly. This is what is done in practice, that algorithm. LJKs are computed, and as we discussed, using this ratio, and they are, this is how they are stored here to find the matrix L. And the transformations LK are applied implicitly. They are applied here. These are the transformations LK, multiplying on the left by the matrix LK, the resulting matrix of the Gauss elimination at step K. And to minimize memory, we can use L and U to be written into the same array as A. So if A originally, for example, was this 3 by 3 matrix, so how can we store? We can store the matrix U as the upper part of the matrix of the storage of the, basically if we think of the memory as this. So the upper part here will store the elements of U, and everything below the main diagonal will store the elements of L. We do not need the elements of L on the main diagonal because we know that they are all ones. So this is in terms of storage. And now to example, we'll do some simple example as to how we perform Gauss elimination. So we start with this matrix, and what we need to do, first of all, if I have to, so let me do it independently of what is written here. So we know that the matrix L is a matrix that will be a 3 by 3 matrix. It will have ones on the main diagonal. Above the main diagonal, it will have zeros, and we have to fill in the element below the main diagonal in the first and in the second column. To fill the elements below the main diagonal in the first column, we look at the first column of A, and we look at the ratio of this element divided by the pivot. So our pivot element here is the top one. This is the pivot element. So we have this element divided by the pivot, and we put it in position 2, 1. So we have minus a half, which is equal to minus 1 divided by 2. So minus 1 divided by 2. And then in this position here, we take this element that stays on the same position in the original matrix A and is divided by the pivot. So we have 0 divided by 2, and it will be on position 3, 1. We end up with 0, and this is 0. So at the first step, we can only compute the first row, the first column of the matrix L. And in fact, we can compute only everything below the main diagonal in the first column. Then we continue with the usual Gauss elimination to make all these elements 0. So what do? We multiply by 1/2 the first row and add it to the second row. And we keep the first row as is. Then we know that when we do that, this element will be 0. Minus 1 times 1/2 plus 2 will give us 2 minus a half, which will give 3/2. And then a half times 0 minus 1 will give us minus 1. This is how we modify the second row. And then we don't need to modify the third row because it already has 0 there, so we just put it down. Repeat it. If we want to use the algorithm, what multiplied by the first row and add it to the third row will make this term 0. Well, it is 0, and therefore we do not change this row. Now from here to go to the next to end up with the upper triangular matrix, before performing the next step of Gauss elimination, we have to fill in the second column of the matrix L. We look to fill the second column of the matrix L. We use only information from the second column of the matrix on the corresponding at the second step of the Gauss elimination. And what we do, we look at this second column and we divide by the pivot element all the elements below the pivot element. So here we have only 1, so we have minus 1 divided by 3/2 will give me 2/3 with a negative sign. So I end up with minus 2 over 3. And this is exactly what the matrix L is. I am done now with the matrix L. And to continue with the Gauss elimination, I save the first row as it is. I save the second row as it is because they are having the corresponding zeros. And now I want to modify this. What do I multiply the second row to add to the third in order to make this term 0? So I multiply by 2 over 3. And when I add, I know that I will end up here with 0. So I have 2 plus minus 1 times 2 over 3, which is 2 minus 2 over 3, which will give me 4 over 3. So I ended up with finding the matrix U and also finding the matrix L. So in this particular case, we see that all the pivot elements, which here are 2 and 3/2, are different from 0, and therefore all the steps of the Gauss elimination can be performed, and therefore we can write the matrix L as a product of the lower unit triangular matrix L and the upper triangular matrix U. And of course, we can check now that the matrix A is indeed the product of the matrix L and the matrix U. Then the next step is to do the operation count. And let's see what are the number of divisions, subtractions, and multiplications here. As I said in your book and in some books, they count only the number of divisions and multiplications because those are the most computationally extensive operations. In some other books, they count the flops, which are the floating point arithmetic operations, and therefore there is a slight difference in the actual number that you end up with, but we are going to do the flops. And so let's first look at step by step what is happening and see what how many divisions, subtractions, and multiplications we have. So if we look at the first step, what did we do in the first step? In the first step, we basically computed all the L's for the first column. To compute all the L's for the first column, we had to divide this number by the corresponding pivot element, the next number by the corresponding pivot element, and so on, the last number by the corresponding pivot element. So as a total, we have a matrix is of dimension m times m. So we have from second down to m, we have m minus 1 divisions, and these m minus 1 divisions were the divisions for the computation of the L's. So we write down for step 1, we have m minus 1 divisions for step 1. Then we'll look at the subtractions, the number of subtractions and the number of multiplications. Once we do that, let's go back to where we were. Once we do that, then what do? We multiply each term here by the L. So this is one multiplication, and add it to this term here, which is one addition. Then this term here multiplied by L, one multiplication, add it to this term here. So to make, we do not discuss what will happen here on the first position on the second row, because we know that this will be 0. This was the way we selected L, so we do not count those as operations because we know that they will be 0 when we even don't perform them. So we have multiplication of each of the terms here, which are m minus 1. So we have m minus 1 multiplications, and we add this to each of those terms here to compute the corresponding elements of the next of the matrix at the next which is going to the next iteration, which will be with upper index 2. So basically we have m-1 addition, m-1 multiplications and m-1, think of them additions or subtractions, doesn't matter. And this is for this row, but we have m-1 row. So for every row we have m-1, and we have m-1 row, so we'll have m-1 squared additions and m-1 squared multiplications at the first step. Now, when we move to the second step, this basically repeats everything. So applied to this matrix, because we do not modify the first row and we do not modify the first column. And if we repeat that for this matrix, these are the same number of computations, with the only difference is that the dimension of the matrix now is not going to be m, but will be m-1. And therefore, if we go down back to where our computation count was, or operation count was, we have that, so we discussed the subtractions and the multiplications, and we also see that at every step is exactly the repetition of the previous step, with the only difference that the dimension of the computational problem is diminished by 1. So if the divisions here were m-1, the divisions here will be m-2. If the subtractions here were m-1 squared, they will be here m-2 squared, because the dimension of the problem reduced from m to m-1. And so on. At the very end, we will end up with everywhere ones. And then if we decide to add all of them up, so we will have the sum of 1 to m-1 divisions, which contributes to this sum. And then the number of subtractions is multiplications will be the same. So this is 2. And then we'll have the sum of 1 plus 2 and so on up to m-1 squared. So we have sum k from 1 to m-1 of k squared. We know that there is a formula for the first sum. We know also that there is the formula for the second sum of the squares of integers from 1 to n. It is a known formula. And using this formula, we end up with this particular equation. Now, we discussed that in this case, we are viewing only the terms with the highest degree. So here we'll have the highest degree 2, m times m. Here the highest degree will be m times this m, and the coefficient, so we'll have m to power 3 as the highest degree, and the coefficient will be 1/3 times 1, because the coefficient in front of m here is 1 times 2. So the coefficient will be 2/3 m to power 3. So the operation cost of the Gauss elimination, and actually of finding the matrix U and finding the matrix L, which we get for free because we have computed all these numbers L that the matrix L consists of. The cost of finding the matrix U is 2/3 m to power 3, where the original matrix is a square matrix of dimension n. And now, how do we solve the matrix, the system AX is equal to B? We think of, you can do it the usual way that you know from linear algebra. You have AX is equal to B. Then you do the elementary row operations until you get to UX is equal to C. And then you solve this with a back substitution. To go from here to here, this is this cost 2/3 m to power 3. And then to go from here to solve for x, this is m squared, and therefore the total cost of solving system using Gauss elimination, since here this power is 3 and this power is 2, and we take the biggest power, is 2/3 m to power 3, approximately 2/3 m to power 3. So this can be done. The problem is the following, that sometimes, not the problem, but there is a little caveat And the caveat consists of the following. If, for example, you have a real world problem that had created for you the system AX is equal to B. And somehow the matrix A that is coming from this real world problem is in a way tied to the design of your whatever you would like to design, the design of your object. And B is something that you have to compute that comes to you, for example, from a customer or from some conditions. And every time you end up solving the system, the same system AX, but with different right-hand sides, BI. So I here, maybe I is not B tilde. So one time you have to solve this system AX is equal to B. Then the second time you have to solve this system for another B tilde, AX is equal to B tilde, but the matrix A is the same, just the right-hand signs are different. There are problems in practice that are like that. If you decide every time when the B comes to solve the problem, every time that when you do that, you will have to do 2 over 3m to the third operations. Then the new B comes, then you have to do 2 over 3m to power 3 operations, and so on. Every time B arrives, you have to do that many operations, because as we discussed, solving a Gauss elimination, solving the system using Gauss elimination is that costly. Now, what you can do is the following. One can, once and for all, if the matrix A is something that is not changing, once and for all, one can make the computation A is equal to L times U. So one can write the LU factorization of the matrix A. And that way, we will have a cost 2 over 3 times m to the third. And this cost will be done, this computation will be done only once, and this computation, this cost will occur only once. Now, if we have the system AX is equal to B, then this system can be rewritten in the terms L times U